go. All right. So today is going to be a really, there's somebody, really important lesson on weak acids being titrated with strong bases. And then I'll do a little bit on weak bases titrated with strong acids. So let me share my screen.
Hello.
Hi. There we go. So I'm going to kind of give an overview first. Then I'm going to kind of show some examples. Like I'm going to work through a whole sequence of calculations. The good news is it's really all review, and it's just tying together a lot of pieces we've already learned. So it's putting it in this context of a titration and a curve. But like I said, it's really things we've already been doing for the last 2 units. So we'll start with, like I said, if we take a weak acid and titrate it with a strong base. So let's look at the key points that define this curve and why they're important to understanding this curve. So the initial solution is just a weak acid. And what we learned about weak acid solutions in terms of their pH was that it's an equilibrium problem. And we also learned that there's a shortcut to that equilibrium problem. And I'm just going to remind you now so it looks familiar. We took the negative log of radical kappa. So hopefully that's familiar, and how we get there is familiar from doing a basic equilibrium problem with a acid dissociation constant, and then based on the 5% rule, being able to reduce it essentially to this. So again, this is a problem we've seen before. But when we're looking at key points of a weak acid titration, that's where we start. We're starting with a weak acid solution whose pH we've learned how to calculate before. At the half equivalence point, we have effectively a buffer, because what's happened is half the weak acid molecules have been converted to weak base molecules. In other words, here's the essential reaction we're doing. This is the neutralization in the titration. At the beginning, all we have are weak acid molecules. But after we've neutralized half of them, we still have half remaining, but we've also created the weak conjugate base in the same solution. And so we have a buffer. And we learned that for buffers, the pH can be calculated using the Henderson-Hasselbalch equation. And if we wanted to pick different points along that equation, we could calculate different pHs. But the main pH that we're interested in is at the specifically half equivalence point. Because what's true is that the amount of the weak base and the amount of the weak acid are equivalent, which is why this logarithm term goes to 0. And then we end up with this special result that at the half equivalence point of these types of titrations, the pH literally equals the pKa. So that's a key point and a real easy one to find. And this is, I'd asterisk this. This is one of the most important points because it's always going to come up in a question about a titration curve, almost always, in one form or another. Then we have the equivalence point. But let's think about what's happened. At the equivalence point, we put enough strong base in to neutralize all the weak acid. So what we've effectively done is converted every bit of weak acid into its weak conjugate base. And since a weak base can hydrolyze, in other words, react with the water and produce hydroxide, that's why we end up with a solution of the weak conjugate base. All the weak acid has been neutralized at this point, and we've created its weak conjugate base. But what we learned about that is that when that's true, it's not at pH 7 anymore. And the reason it's not at pH 7 is because we have a weak base solution. So our pH is going to be greater than 7 at the equivalence point. That's another key discovery, that for a weak acid being titrated with a strong base, the equivalence point doesn't happen at pH 7. It happens at a greater pH than 7. Again, simply because we have a weak base now in the water, which can hydrolyze and generate a little bit of hydroxide. So for that, we're going to have to use some other skills that we learned. We can find the pOH because we can do effectively what we did for the pH equilibrium, which is the shortcut of negative log radical kubba. And again, the base constant is going to be found by doing Kw over Ka. See, these are, again, all things we've done before. This is nothing new, really. We're just tying it all together. And then, of course, once we know the pOH, the pH is just 14 minus that. And then finally, once we've gone beyond the equivalence point, not only have we got rid of all our original weak acid, but now we have leftover strong base, and that's going to dominate the solution in terms of the effect on pH. So this last point, all we're going to have to do is find the pOH by taking the negative log of the excess hydroxide concentration, and then we can find the pH by doing 14 minus that. So like I said, I'm going to kind of walk through this entire set of calculations with one example, and then we'll apply it to a few other things to see how it looks. And then on the weak base side, let me just show you that it's really the same problem, but just coming at it from the other direction. So even though I'm not going to go through all the calculations on this one today, I just want to show you how similar it is and why really, if you understand the first one, the second one is almost the same. So remember, if we start with a weak base and we add a strong acid, this time our reaction looks something like this. Weak base, strong acid would be something like hydronium, and then we would get our weak acid conjugate and water. So again, it's just the reverse of the one we did on top. But since we're starting with a weak base solution, this time we begin kind of where we left off at the equivalence point here. We find the pOH first by taking the negative log of radical kubba, and then the pH is just 14 minus that, just like before. So again, it's the same type of calculation. We're just doing it first because we're starting with a base solution, a weak base. The equivalence point, exactly the same as before. Here again, we just note that the pH equals the pKa because the logarithm piece falls away just like it did before. So let me just repeat it. So even though we started with base, halfway through the neutralization, we have equal moles of weak base and weak acid. So this statement is still true. And this logarithm goes to 0 again, and once again the pH equals the pKa. Now you have to be careful, because if you're starting from a base, you may have to first find the Ka again by simply doing the Kw trick. Not a big deal otherwise. Same kind of problem. Now at the equivalence point, again, another really key discovery is that since we have neutralized all the weak base at the equivalence point and converted it all to its weak conjugate acid, we expect this equivalence point to occur at a pH less than 7. Why? Because we have a weak acid, and that weak acid is now governing the pH of the solution. So when we have a weak acid, we know what to do. Oops. We just take our shortcut, our equilibrium problem, reduced to the negative log of radical caca, just like we did at the first point in the last problem, because again, we're doing the same thing. We're just finding the pH of a weak acid solution. And finally, when we go beyond the equivalence point, all we have to do is take the negative log of the excess strong acid that we put in. So as you can see, both of these types of problem are almost the same. Just in one case, we're starting from a weak acid and working it through by adding a strong base. And in the other problem, we're starting with a weak base and working it through by starting it with a strong, or titrating with a strong acid. And like I said, if you look at the little equations I put up here, these are all problems we've already done. We're just stringing them together. So it shouldn't be that bad. All right, let's do an example to see how it actually looks. So I created this little grid. I know it's hard to read probably from your screen. Let me zoom in a little bit more maybe. On the left side, I'm going to show my work. for each key point that we just talked about. And then on the right side, I'm going to plot the titration curve. So I have the pH on this axis. I have the milliliters of sodium hydroxide on this axis. And then here I'm just giving the title that we're titrating a weak acid with a strong base. So in our example, we're going to do the following titration. We're going to titrate, well, or we're going to watch it jump around. Sorry, always a risk in these things. My technology just laughs at me sometimes. You know how it is. So we're going to titrate .50 milliliters of 0.1 molar acetic acid with 0.1 molar sodium hydroxide. And I picked this to be really simple math and really kind of symmetrical because I have equal concentrations. The reaction is effectively 1-to-1, and I don't know why this keeps moving, so what I'm going to do is I'm going to get rid of this table because I think that's what's killing me here. I mean, I don't think this program likes to, oh boy, okay, work within the table confines here, so I'm going to just get rid of this, sorry. Start that again. I'll just leave this here. And I'll work off to the right. Okay, so as I was saying, I'm going to titrate. Yeah, I think it's just this program doesn't like me when I write in the tables. I'm just going to write it again. 0.1 molar acetic acid, and we should add the Ka for this. The Ka is about 1.8 times 10 to the minus 5, and we're using 0.1 molar sodium hydroxide. Okay, so the first key point that we need to consider is the initial point. So 0.1 is what would be the initial pH. Well, this is actually what we just said, a very simple problem based on what we're given. The pH is just going to be the negative log of radical Ka. Ka is 0.1 molar, because that's what we have at the beginning. And Ka is the equilibrium constant, the acid dissociation constant, which we also know. And if we simply calculate that number, we get the first pH, which is about, let's try that again. I missed. I can't hit the buttons. Sorry about that. 2.87, let's say. So what this is telling me is that when I first put this solution in a beaker and I put in the pH meter, it reads 2.87. So at 0 added volume, my first point is somewhere around here, just under 3. Cool? All right. If you have a question, just jump in. So our second point, we said, is the half equivalence point. And again, because we're picking this specific point within the buffering region, it's really simple. But let's kind of prove, or well, not prove, but let's show what volume this happens at. So I'm going to set up kind of an equation at the bottom to work from consistently. So I'm going to use the generic notation of weak acid plus strong base makes weak conjugate base plus water. And again, I want to work in millimoles just because it makes life easier. So we know that the HA starts with 50 milliliters, and we know it starts at 0.1 molar. And when you multiply those, you get 5 millimoles. That's how much total acid, weak acid molecules were in our original solution. Our base is 0.1 molar, but we don't know how much we're using. We're kind of adding it as we go. But here's my question. Just based on the symmetry of the problem, If I want to reach the half equivalence point, how many millimoles of strong base do I need to add to neutralize half of the acid?
2.5.
Exactly. 2.5 millimoles brings me to the half equivalence point. Now, by the symmetry of the problem, you can already see it's going to take 25 milliliters to do that. But if the problem was not symmetrical, like if I had a different concentration, I could just divide the millimoles by the molarity, and I'd get back to the volume. Now, the pH at this point we said is simply equal to the pKa. But the pKa is just the negative log of Ka. And when we do this calculation, we find negative log of 1.8, about 4.74. So that means if we go back to our titration curve at about 25 milliliters, which is halfway through the titration, we've only gotten the pH up to about 4.74, so somewhere around here, let's say. Okay. The third key point we talked about was the equivalence point. Now this is the stage at which we've added enough base to neutralize all the acid. So let's go back down here and adjust what that has to be. So I think we'd agree that for neutralization, complete neutralization, we would need 5 millimoles of the strong base, which would have taken 50 milliliters of the hydroxide. But here's the key point. When we do this, we use up all 5 millimoles of the weak acid. We use up all 5 millimoles of the strong base. But even though we technically started with none of the weak conjugate base, we're adding 5 millimoles to that just by sheer stoichiometry. Make sure that makes sense. Because that's the key point. Now when you think about this, we can calculate the concentration of the weak base in this mixture because the total volume is now 100 milliliters and there's 5 millimoles of base in it. So that means that we now know that the concentration of our weak base is 5 millimoles out of 100 milliliters, which is just 0.05 molar. So now we know the concentration of our base at this point. To solve our shortcutted equilibrium problem, we're also going to need to know Kb. But what we know is that that's just Kw divided by Ka. Sorry, I'm crisscrossing my capitals and lowercase and it's bugging me. I have my own quirks, what can I say? Okay, so here we're just going to take our water constant, divide by our equilibrium constant for the acid. Again, all things we've done before. And I'm out of room, so I'm going to squeeze it down here. We get about 5.6 times 10 to the minus 10. So what this lets me do, remember, is find the hydroxide concentration through radical kuba-kuba. But I can get directly to the pOH by taking the negative log of that. So I'm basically just going to do this calculation. You see the numbers, so I'm just going to plug them in. When I do this, my pOH comes out as follows. Negative log, square root, 0.05 times 5.6 times 10 to the minus 10. I get about 5.28. But that means I can now find the pH because it's just going to be 14 minus the pOH. So since we just found that, we're going to take 14 minus 5.28. We get about 8.72. And that's consistent with the fact that we expected the equivalence point to happen in a pH greater than 7. This is showing why. This equivalence point pH being greater than 7 is because our weak base solution hydrolyzes. Remember, that means it reacts with the water, and as a result, it generates some hydroxide. And that's why my solution now is basic at the equivalence point. Now that happened at 50 milliliters, and that's where we jumped up to 8.7 or so. So let's say about here. Looks like 8.7, something like that, right? At this point, we just have one more calculation to go. So we said that the fourth point is going to be when we've gone past the equivalence point. So I'm just going to pick an arbitrary value that's past it, just for the sake of argument. Oops. So beyond the equivalence point. And for my purpose, I'm going to add a total of 100 milliliters of base. Just again, so I have a number to work from. Typically, we want to pick one that's far enough away so we see a big enough difference. So I'm going to go 100 here. Watch what happens when I do that. This becomes 100. And let's follow all the changes that occur because of that. Sorry, I'm lagging a little bit here. Now at this stage, that means our millimoles of base have gone up to 10, meaning our strong base. When that's true, we still use up all of the original acid, but you'll notice there's 5 millimoles of strong base left over. You might say, oh, but there's also 5 millimoles of weak acid. That's true, but the weak acid is going to do almost nothing. I'm sorry, weak base. But that's true, but it's going to do almost nothing compared to this leftover hydroxide. So the key point, as we said earlier, is it's the excess strong base that really dominates. So I need to know its concentration. Well, I know the total volume is 150 now, right? So to get the concentration of hydroxide in the solution, I'm just going to take how many millimoles of it are left over, and I'm going to put it over this total volume. And when I do that, I find about 0.0333, whatever. Okay, I can do better. Hold on. Sorry. I can do better. 0.33 molar. So now to find the pH is really simple because the pOH is just the negative log of that concentration of hydroxide, which is 0.033. And when I do that, I get about 1.48. And then 14 minus that gives me the pH, which is about 12.52. And that happened after I added 100 milliliters. So I'm going to have to scroll up a little bit here, maybe. Okay, here we go. So here's my 100 milliliters. I'm going for like 12 and a half, so somewhere around here. And now we can sketch the curve. So if we're looking at this titration curve, here's the typical way they look. There's an initial pH, there's a little bit of a bump up, then there's kind of a steady increase until we reach the equivalence point, which we pass through at a pH greater than 7, and then as we continue to add more base, it creeps up to a higher pH. So if you recall, this looks quite a bit like the one we did last time, the strong. But let's look at the key differences. So I'm going to make some labels here. At the beginning, all we have is the weak acid. So let's label the molecules that are primarily present, excluding the water, which we know is everywhere. So at the beginning, we have mostly just weak acid. At the half equivalence point, or really within the buffer region itself, we have a mixture of weak acid and weak base. By the time we get to the equivalence point, it's all become weak conjugate base primarily. And then when we get beyond the equivalence point, the key is this excess hydroxide that is driving everything. Remember again the key points, 1, 2, 3, and 4. Point 1, the initial solution. Point 2, the half equivalence point where pH equals pKa. I cannot emphasize this enough. I'll write it in just again. Point 3, the equivalence point. And what I can't emphasize enough here is that for a weak acid being titrated with a strong base, the pH is going to be greater than 7. And then of course point 4 where we have just the excess base. So let me pause there and see if you have any questions so far. Anyone? Anyone? Bueller? Bueller? Okay. So I want to kind of show you a couple things here. First of all, in terms of picking an indicator, we had said last time that if you're going to choose an indicator that tells us when the titration is done, the endpoint, you have to pick one such that the color change happens as close to the equivalence point as possible. So if we picked, for example, methyl violet, this would not work very well because our pH would have changed too early and we would have seen a color change before we hit the true equivalence point. Since our pH needs to be basic, Miriam, it's almost going to asymptotically approach a limit, right? Because as we're adding more and more base continuously, it's going to level off more and more, but it'll never reach kind of the end theoretically. It's always going to approach a limit. But we're never going to go that far anyway, to be honest. So which of these indicators makes the most sense? Like based on the titration we just showed, which indicator do you think might be a useful one to indicate for this reaction? So you're looking for the pH at the equivalence point as the key indicator.
Probably phenol red, phenolphthalein.
Yeah, something around here, right? And just to emphasize this more clearly, there's a couple of ways to look at it. If you have a table where it shows you the pHs, you just go by whatever's closest to the pH at the equivalence point. And even if it's generic and you haven't calculated it, you can just get at least close, right? Like if you see it's going to be basic, like in the case we just did, you're looking for something where the pH color change happens at a pH of around 8 or 9. If you're given Kas for the indicators, you just find their pKas, which effectively is going to be the same idea. So let me show you a cool way to see this. I have this other program that lets me kind of paint picture. So here's my acetic acid. It's 0.1 molar, and we started with 50 milliliters. Watch this. I'm going to review every calculation we just did. Here's my sodium hydroxide. It's 0.1 molar. If I don't add any sodium hydroxide, that's my initial solution is about 2.88. I think we had gotten 2.87. Okay. At the half equivalence point, when we've added 25 milliliters, the pH has reached about 4.76. Close enough to what we got, I believe. At the equivalence point, when we've added 50 milliliters, our pH hits about 8.7-ish. And finally, when we go beyond the equivalence point to 100 milliliters of base, we had calculated about 12.5 for our pH. So again, this little program lets me get the calculations really fast. Let me go back to the equivalence point to make my point about indicators. So this also lets me look at the indicator and the curves. Check this out, it's really cool. So if I took this database, it lets me kind of click through a bunch of different possible indicators I could have used. As I'm clicking through it, let's say what would have happened if I would have used something like, I don't know, phenol red. Or let's do a different one. Let's do methyl violet, I think is the one I had indicated. And let's tell it to show us where the transition happens on the titration curve. Check this out. It's kind of cool. So if you notice, here's our titration curve that we just built together. Here's the pH at the equivalence point around 8.7. Look at where the transition for the color change happened here. Way down here at a pH of like 1 or 2. This would have been so useless as an indicator because it would have changed like right away. And we wouldn't have even seen anything useful. Let's kind of go up and down the list here just to get an idea of how this works. If I had picked, let's say, methyl orange, notice that it's closer, right? Our transition happens somewhere here, but we're still way off of where we need to be. In other words, we would have stopped our titration like here at a very low volume, thinking, oh, look, it's done. But it's not done. We haven't hit this point yet. Let's hit another one. I think somebody had said phenolphthalein, so let's check that one out. Boom. Notice where the transition in color happens. It's colorless below this pH, and then it changes pink. Notice that happens almost completely centered on our equivalence point. This will change color right when we want it to. It'll change color just as we're transitioning into the equivalence point, and then it'll tell us to stop at an accurate point of volume addition. Does that make sense? Like how this is showing that, or? Okay? So that's what this is about. Here's another cool thing. I'm going to scroll down for a moment. I want to see if you can see the difference between this curve and the one I'm going to show. How is this curve different than the first one? Can you tell? Same equivalence point.
It's going from more basic to acidic.
Yeah, so all this curve is showing is if I had started with the base in the beaker and added the weak acid to it, it would have just gone in reverse, right? It would have slowly become lower and lower in pH, gone through the equivalence point, and then dribbled down to a lower and lower pH. So it's just really just flipping which one you're adding to which one. But you can see it's really the same idea. The calculations are just backwards. So anyway, I just thought that was cool that this program lets us check that out. One more cool thing in terms of comparison, and then we'll look just a little bit at some examples to try. So in this graphic, you see that we're comparing a strong acid, strong base titration, which is the one we did last week, which is showing this very sharp jump at the equivalence point, like almost 10 units of jump. The weak acid jump is less. And notice that for the strong acid, strong base, it passes through 7 at the center of the jump. But when it comes to the weak acid, it jumps centered on a pH that's greater than 7. To make this more emphasized, check this out. This shows a whole different series of acids being titrated with a strong base. Here's the strong acid, strong base. And what you see is the Kas are getting smaller. The reason I'm showing you this is to indicate that the weaker the acid we start with, the less clear the jump is, meaning the jump at the equivalence point is going to get narrower and narrower. So I just think this is cool because it really shows it. So the weaker the acid, the higher the pH at which the equivalence point happens, which makes sense. Because if it's a weaker acid, it has a stronger conjugate base. And if it has a stronger conjugate base, then at the equivalence point, the pH will be even higher. So all of these things, again, connect to stuff we've already learned. Now let's look at a little simulated experiment and see what you can figure out. So in this experiment, we're going to determine an unknown concentration via titration. So to do that, we have our burette, in which is the sodium hydroxide. We have our acid in a flask with a little stir bar. And then we have a data table where we're plotting the pH, and a graph where we're, data table where we're recording, and then a graph where we're plotting. So I'm going to change the concentration of base to 0.5 molar, and then we're just going to add it. And let's see if we can figure out what the concentration of the acid is. That's what we don't know. We know we're testing 25 milliliters of the acid. We just don't know what the concentration is. So check this out. I'm going to start dribbling it in, and you can see the titration curve forming. This is kind of what the experiment would have looked like if we did it live in person, except not a cartoon. It would have showed a similar kind of change in the pH, and we would have seen it plotting as you're seeing it now. And then we'd be looking for this jump through the equivalence point, and then we would have let it run a little bit extra just to see the full definition of the curve. Okay, so here's our curve. And let's think about the data analysis part, because that's the part that matters really here. So let me put up a new page. Oopsie. Hey. What the? Sometimes things just don't go the way you want. Alrighty then. Okay, so here's the data. Let's record what it says. What we know is that this was a reaction between and again, I'm just going to write generically if that's okay, a weak acid and a strong base. I just find it's easier to write it in a generic form each time because, well, it just saves time, especially when the molecules are big and complex looking. We know that we had 25 milliliters of the weak acid in the flask. We don't know its molarity. That's our goal. We want to find it. The hydroxide we know was 0.5 molar, but how much did we use to reach the equivalence point? That's where using the graph matters. There was a homework problem this last time, similar, right? So you're going to look near here and say, okay, well, what's that volume? It looks like it's about 37. But let's look a little more carefully. Since we're looking for the big jump in pH, if we scroll on the table now, check this out. I'm looking for a big leap. Oh, I think I found it. And we're pretty close, right? It's around 37, between 37 and 38. You can see the big leap. So I'll just take 38, call it a day. Close enough. So it turns out 38 milliliters of hydroxide were needed to neutralize this much acid. Now it's a real easy stoichiometry problem. Because if I multiply these two numbers, I can get the millimoles, which in this case is 19. But this is a 1-to-1 ratio, right? So that means there must have been 19 millimoles of the acid in this volume. So I can now show the concentration of the acid by just dividing these two. The millimoles of the acid by the volume, and I get about 0.76 molar. So the point or the moral of this story is when we're looking at a titration curve, I don't care if it's weak or strong, the stoichiometry of equivalence is the same process. It's just a solution stoich problem where we use the graph to find the volume of what was added. And then from its concentration, we find the moles, etc. If we're right, this will tell us. Let's see, 0.76. Feels so good to be right. Any questions about that application? You guys are killing me with all these questions. Just kidding. All right. I'm going to go and do a different experiment. This time I want to find the pKa. There will never be a weak acid, weak base problem. There's just no practical reason. The only thing we will do is weak with strong. So if it's a weak acid, there'll be a strong base. And if it's a weak base, there'll be a strong acid. And obviously strong, we already did. I will just talk about the weak base in a moment, but just to generically show the graph. First, let's see if we can solve this experiment. This experiment wants us, and again, I'm going to increase the concentration of the base, wants us to figure out the pKa of the acid. Okay, let's see what we can do. So once again, I'm going to, oh wow, that was too concentrated. Let's start with 0.1 molar. I think that was too much. Okay, that's better. Oops, boing. So where should I look if I want to find the pKa of the acid? How do I know where that happens?
Isn't it at the half?
Yeah, equivalence point. Exactly. And that's somewhere around here, right? So the way to do this more accurately, though, is go to your equivalence point, and whatever that volume is, you're going to go to half the volume to find the true half equivalence point. Again, it's hard to read on this graph, so I'm going to use the data table. I'm looking for the jump. The jump here happened at around 12, so between 7 and 10, right, there's the jump. So if that's the case, the half equivalence should have happened at around 6. Now that means the pH was 5.89, which looks reasonably good. And so the pKa is also 5.89. And that's all we have to do with that. Oops. And that's how simple that application is. It's just a question of knowing how to read the graph and knowing those key points. All right. So last but not least, let's just really quickly sketch a weak base plus a strong acid. And again, I won't go through the calculations this time. I'll go through them next time if we need to, but I think there's some in the homework for you to try. Either way, if we're doing a weak base titrated with a strong acid, again, I'm just going to sketch it. So this time it's the volume of acid added. Clearly we would start at a higher pH. Let's call this 7. The pH would first creep down a bit. Then our equivalence point jump would happen at a pH centered less than 7. And then if we kept adding acid, it would trail off again. So here's our equivalence point. Here's our half equivalence point. And here's our beyond equivalence point. Here's our initial. And again, let's just kind of lay out what this would look like. If we started with some generic base, we'd be adding hydronium, and the products would be weak acid and water. And again, we could go through the math, but we're not going to now just because I don't want to take that much time. I just want to indicate what would be present. At the beginning, we'd have primarily just a weak base solution. At the half equivalence point, it is still true that the pH equals the pKa. So notice we're getting the Ka of the conjugate acid of this weak base. And this is because we have both the amount of base and acid, weak base equivalent. At the equivalence point, it's all become weak acid, and beyond the equivalence point, it's primarily hydronium. But other than that, this looks really similar to what we just did. Mathematically, it's just similar types of problem solving. And that's really it. So, do you guys have any questions before we end this? And I do want to tell you I really appreciate your attendance, so I'm going to give you a bonus. So don't go away. Let me mark that you're here. You get some extra credit for your extra attendance. So who's here? It's Noshin. And Mr. Steven and Miriam and Caitlin. That's worth a bonus. Oops, that should be exclamation point. Woohoo! You're welcome. Thank you. I appreciate your time. And I'm just going to add one last point is the assignment you're supposed to work on is just to finish the rest of problem set 3. It's already posted that way, but it should be now quite doable because you have the full background to do it. So that's it. I will see you next time.
Thank you. Bye.
Thank you. Have a great day.
You too.
See you. Have a good day.
Thank you. Bye-bye.